Hello, this presentation is part of my study on antenna and today's topic is gain of antennas. Alright, let's talk about gain, which is an essential antenna parameter. First, it defines gain as being similar to directivity, but it also takes into account antenna losses. In simpler terms, it tells us how well the antenna can convert the accepted power into radiated power, considering real-world losses. Mathematically, gain is expressed as gain theta phi equals 4 pi u theta phi by P accepted, where P accepted is the power actually accepted by the antenna from the source. Gain is related to directivity by the equation G equals ECD into D, where ECD represents the radiation efficiency of the antenna. Radiation efficiency is defined as the third equation, where Rr is the radiation resistance representing the part of the power that is radiated. RL is the loss resistance, which accounts for energy dissipated as heat and other losses. Finally, it's important to note that gain can sometimes be less than 1 due to significant losses in the antenna structure. This understanding of gain helps us evaluate and design antennas that perform efficiently in practical scenarios. Now let's understand how power flows through an antenna system. First, we begin with input power, which is the power supplied to the antenna. Some of this power is reflected back due to impedance mismatch, so it doesn't get radiated. What remains is the accepted power. But even then, not all accepted power gets radiated. Some is lost due to losses like heat or imperfect materials. The rest is radiated power, which is what we actually want for efficient antenna operation. Second, to quantify the mismatch between the antenna and the transmission line, we use here the reflection coefficient, the first equation, where Z is the antenna impedance and Z0 is the characteristic impedance of the transmission line. Third, let's talk about radiation efficiency, represented by ECD. It defines this the second equation. Here P radiation is the radiated power and P accepted is the power actually accepted by the antenna. Finally, remember that lossy antennas which have significant internal losses will have a gain that is less than the directivity. Understanding these factors helps us design antennas that efficiently convert input power into useful radiated power, minimizing losses and maximizing performance. Now let's compare directivity and gain to better understand their differences. First, let's look at the numerator. Both directivity and gain use U theta phi, which represents the radiation intensity in a given direction. Second, the key difference lies in the denominator. For directivity, we use P radiator, which is the total power radiated by the antenna. For gain, we use P accepted, which is the total power accepted by the antenna, accounting for any losses inside the antenna. Third, in terms of efficiency, directivity doesn't include losses. Gain does include losses, so it's always lower than or equal to directivity. Finally, let's consider the typical range. Directivity is always greater than 1 because it's a measure of how well the antenna focuses energy. And gain, however, may be less than 1 if the antenna is very lossy, meaning it radiates less effectively due to internal losses. This table helps us see why gain is often preferred in real-world antenna analysis, as it reflects both the antenna's focusing ability and its efficiency. Alright, let's wrap up with a quick example calculation of gain. First, let's look at what's given. The directivity D naught is given as 1.5. The radiation efficiency ECD is given as 0.4. Next, we calculate the gain. Here we use this formula G equals ECD into D naught. So total is 0.6. Finally, let's convert this gain to decibels. So use the last formula, and this shows us that even with a directivity greater than 1, the gain can be less than 1 due to the antenna's efficiency, highlighting the importance of efficiency in practical antenna design. Let's now look at absolute gain, which is another important concept when evaluating antenna performance. Absolute gain considers both antenna structure Losses. These are losses that occur within the antenna itself due to materials, imperfect conductors, or other factors. Mismatch losses at the port. These are losses due to impedance mismatches between the antenna and the transmission line or source. This means that absolute gain provides a more realistic measure of how an antenna will perform in a real world system, as it accounts for both internal and external losses. So, absolute gain is especially useful when we want to predict how an antenna will behave well actually connected to other devices, like in communication systems. Now, let's walk through an example of calculating total radiated power from a given radiation intensity. So here the given radiation intensity U theta phi is defined as the first equation. To find the total radiated power per radian, we integrate U theta phi over all directions, and the second equation is the radiated power equations. So next we will evaluate this integral step by step, which helps us understand how the radiation is distributed in space and determine the total power the antenna radiates. This process is crucial for connecting the theoretical radiant intensity to the actual radiated power of the antenna. Now let's break down the integration steps we need to find the total radiated power. First, we integrate over phi. The first equation is the simply accounts for the full circle around the antenna, and second, we integrate over theta using sine cube theta. For this, we use the sine to the power 3 theta equation, and this identify helps us simplify the integral. And finally, after evaluating the integral, we get P radiation. This gives us the total radiated power from the given radiation intensity. This step-by-step evaluation helps us connect the mathematical expression to the physical quantity of radiated power, giving us a better understanding of how antenna performance is quantified. Now, the calculating the directivity of the antenna radiation, and first we use the formula of directivity d theta, and this compares the directional radiation intensity to the total radiated power. And next, let's substitute per radiation from the previous slide. Recall P radiation equals P radiation equals 8 pi a naught by 3, and plugging that in, we get d theta equals 4 pi into a naught into sine squared theta by 8 pi a naught by 3, and simplifying, we get d theta equals 3 by 2 into sine squared theta. Finally, the maximum directivity occurs at theta equals 90 degree. Here sine square 90 degree equals 1, and so d max equals 1.5. Let's demonstrate how directivity varies with angle and shows the peak directivity value. Finally, let's consider how gain is affected by efficiency. Given here the radiation efficiency ECD equals is 0.9, so using our earlier directivity result of 1.5, we calculate the gain G theta equals ECD into D theta. So plugging the values here, G theta equals 0.9 into 1.5 into sine squared theta. So this simplifies to G theta equals 1.35 into sine squared theta. This shows that gain is always lower than directivity due to losses, like resistance or imperfect materials inside the antenna. Understanding this difference is crucial for designing and analyzing real-world antennas. Now, half power beam width, which is the key parameter for antenna performance. First, we find the angle theta where the directivity drops to half its maximum value. Since d max equals 1.5, then d theta equals 1.5 by 2 equals 0.75. Next, we solve for theta. From earlier, the theta equals 3 by 2 into sine squared theta. Setting that equal to 0.75, sine squared theta equals 0.5. This gives us theta equals 45 degree and 135 degree. Finally, the half power beam width is the difference between these angles. 135 degree minus 45 degree equals 90 degree. This tells us that the antenna's power is concentrated within a 90-degree beam, which is a key design factor for focusing energy. Let's conclude with a visual summary of the key concepts we have discussed. Top left, we see the spherical coordinate system, which helps us define the radiation pattern in terms of theta and phi. Next, on the top middle, we compare gain and directivity using a simple bar chart. It shows that gain is typically lower than directivity because it accounts for losses. Top right, we have a directivity plot as a function of theta. You can see that Dmax occurs at 90 degree, which matches our earlier discussion. Bottom left, we show the reflection coefficient diagram illustrating how impedance mismatch between Z0 and ZA affects power flow. Bottom center, there's a power flow diagram. It starts with input power, some of which is accepted power by the antenna. Losses reduce the power that's actually radiated. Together, these visuals reinforce the relationships among directivity, gain, efficiency, and how they all contribute to understanding antenna performance in real-world systems. So let's wrap up with the key takeaways from today's presentation. First, directivity shows how focus an antenna's radiation is in a particular direction, assuming no losses. Second, gain takes into account the losses, making it a more practical measure for real-world antennas. Third, radiation efficiency serves as the bridge between directivity and gain. It shows how much of the accepted power is actually radiated. Fourth, let's talk about real antennas. Directivity is always greater than or equal to 1. It's a purely directional parameter. And gain, on the other hand, can sometimes be less than 1 because it accounts for losses inside the antenna. Finally, in measurements and in practice, we often focus on gain because it's easier to relate to port power, the power actually delivered to the antenna. Understanding these points helps us design and evaluate antennas more effectively in real world applications. That's it all for today. Thank you.